like
Judge me.
halfway there.
There we go.
Okay. Yesterday we talked about review for Unit 1. Any questions on that? Nah? Okay, so today we're going to do Unit 2 review. So this is all about polar form of a graphing in equations, and also it dealt with vectors and things having to do with vectors. Okay, so we started just talking about graphing polar points. Okay, so remember the idea with graphing polar points is instead of having an x and a y value, you have r and theta. Okay, and the graph paper, remember, it looked like concentric circles. If you want to borrow some graph or take some graph paper, it's back there. And so the r value tells you how far away from the pole to go, which is like the origin. So this is how far from the pole. And the theta value is the angle of rotation. And remember, the idea here is that you can have positive or negative r values, and you can have positive or negative theta values. If r is positive, that means you start by moving to the right of the pole. And if r is negative, that means that you start by moving to the left of the pole. And if theta is positive, that corresponds to a counterclockwise rotation. And if theta is negative, that corresponds to a clockwise rotation. Okay, so for example, if I wanted to plot the point 3, negative 5 pi over 4. Remember, this is in radians, so you have to kind of remember how that works. So negative 5 pi over 4 radians, you would multiply by 180 over pi, or the shortcut is you could just replace pi with 180, and that would work as well. So this ends up being negative 225 degrees, right? So to plot this point on your polar graph paper, you would just go 3 over to the right, and then rotate 225 degrees clockwise from there. So it's going to be like going this way, 225 degrees would end up right there. That would be the point. It's a lot easier to stay on track if this is polar graph paper. But yeah, this distance away from the origin, from the pole, is 3 still. Everybody good with that? So the angle might have positive or negative r's and thetas, and it might be in degrees or radians, and you need to be able to do any of those situations. Any questions on that?
I'm just wondering, like, in that case, could you do like 360 minus 225 to get like just the positive version of that and do it clockwise?
Sure, yeah. Would that be easier?
I don't know. I can just find in my mind just like I don't like seeing negative.
Okay, yeah, it's definitely the same thing. Those are coterminal angles. Remember, coterminal angles are just angles that end up in the same place. So as long as you use a coterminal angle, that's another important thing about polar points is there's more than one way to express it always. Unlike rectangular coordinates where you can only get there one way, like right a certain amount, up a certain amount or whatever. Here, you can change theta and r and however you want, as long as it ends up in the same spot. There's lots of different ways to get there. Okay? Then we talked about going from polar to rectangular form and vice versa. So there were 4 formulas to go from one to the other, okay? There was x equals r times cosine theta, y equals r times sine theta, r equals the square root of x squared plus y squared, and theta equals inverse tangent of y over x. So these formulas, these 4 formulas, are all based on the same idea. If you have a point in space, like this point over here, for example, you can label this triangle. This is the x value, this is the y value, this is r, and this is theta, right? So to get these first 2 formulas, you're just doing SOHCAHTOA. Like the sine of this angle is opposite over hypotenuse. That's what this equation is saying. The sine of this angle is y over r, but it's just solved for y. The cosine of this angle is adjacent over hypotenuse. That's this formula. The formula to find r is just the Pythagorean theorem. And this is just the tangent function. The tangent of theta is y over x. So theta is the angle whose tangent is y over x. Does that make sense? So these formulas are easy to get if you just remember this is the picture. But remember, you don't have to memorize any of this stuff. You can just refer to your notes, okay? So the first 2 formulas are the formulas to change from polar to rectangular form. And the second 2 formulas are to change from rectangular to polar form. And remember, I'm going to put a little asterisk next to this, because sometimes you'll do everything correctly, but you'll get a point that doesn't quite end up in the right spot, but it's like directly across from where it should be. So you have to just make sure that when you change a rectangular point into polar form, it ends up in the right spot. If it doesn't, you have to use reference angles or something to adjust it. Does everyone understand what I'm saying? You want me to do an example like that, or? Yeah, I will. Okay, so how about something like, what if I have a point like -2, -3 in rectangular form? And I'm trying to change it to polar form. So according to these formulas, r would be the square root of 4 plus 9, which is radical 13. And theta would be the angle whose tangent is 3/2, which I could do that on my calculator. I want to make sure my calculator is in degrees. This calculator is not. So I'm going to change it to degrees. So if I find, whoops, I forgot that inverse symbol, the angle whose tangent is. So if I take the angle whose tangent is 3/2, I get 56 degrees roughly. So this is a perfect example. Like if I were to go radical 13 over, like this is radical 13, and then rotate that 56 degrees, that definitely doesn't end up in the right spot, right? I know that the point 2, -3 is actually down here. So this is an example where you have to adjust. You'd have to say 56 is actually the reference angle, not the actual angle. The actual angle would be 180 plus 56, right? So theta is actually 180 plus 56, which would be 236. Does that make sense? Or another way you could adjust it is instead of going to the right radical 13, I could go to the left radical 13 and then go 56 degrees. That would work. Or r is negative radical 13. One or the other. You wouldn't do both these things because then you'd still end up in the wrong spot, right? Everyone understand what I mean? Okay, so that's changing from one form to another. Then we talked about polar graphs. And there were lots of cool looking graphs that you could get using polar equations, right? They included interesting things like cardioid, lemniscus, limison, a spiral.
I think Rose was one.
Yeah, rose, thanks. Right, so you just need to know what these things look like. A cardioid is like kind of like a weird looking heart like that. A lemniscate is like a infinity symbol. A limison kind of looks like a cardioid. The difference is a cardioid, the point of the heart is right at the origin, and in a limison it doesn't pass through the origin at all. There's also a limison with inner loop, which kind of looks like this. That's also a type of limison.
So can that like never happen for a cardioid?
This?
Yeah.
No, this is called a limison with inner loop.
So if it was like centered at the origin and it had like a loop, it would
Yeah.
still be a limison?
That's weird, right? That should be called a cardioid with inner loop, but it's still called a limison with inner loop. That's a great question. And then a rose is just like, not really a rose, it's more like a daisy. If my botany is correct. Okay, so that's the different types of curves. You just have to be able to look at it and say, oh, that's what that one is. That's it, okay? And I think that was it for polar stuff. And then we started talking about vectors, which are not unrelated, right? Vectors, there's a lot of things that are kind of the same idea. So we have vector, first of all, like putting a vector in component form. So that's graphically what that's doing is if I have a vector and it looks like this, right? It's just taking that vector and moving it like to the origin, like that, right? If it's over here to begin with, it's just taking it and moving it. So it keeps it the same length as the magnitude, and it's pointing the same way, direction. Magnitude and direction are the same, but now it starts at the origin, right? So that's how you would do it. Graphically, you could do it using slopes, right? Like you could just say, well, what's the slope of this line? If this vector has a slope of like, for example, 2/3, then I'm just going to start at the origin and just go up 2 and over 3. And it's going to end up giving me an equivalent vector in component form. That's one way to do it. Another way to do it was algebraically. Sometimes they'll give you the starting and ending point of a vector and ask you to put it in component form. So if they said the vector is from 2, 5 to -1, 3, and they said put this vector in component form, this is one way, right? You could plot these 2 points and actually physically move the vector. That would work. What's the other way to do it? Do you remember? Yeah, you subtract the components. You're just going to take the x values and subtract them, but it has to be a particular way. Anybody remember which one is which? Is it -1 minus 2, or is it 2 minus -1? No, it's the other way around. It's -1 minus 2, I think. And then it's 3 minus that, so it's -2. Let's just verify that graphically. So how you could verify that graphically is actually plot the 2 points. So if I have 2, 5, that's that point, and -1, 3, -1, 3, that's that point. So this vector looks like this, right? If I were to take this vector and move it to the origin, oh, it's not working like it did. Oh, there we go. You can see this ends up being correct. You're going left 3 and down 2. If I had subtracted them in the other order, I would have gotten +3, +2. That would definitely be pointing the wrong way, right? So if you're going to do it this way, you just have to remember that you're going to take the ending point first in the subtraction. So it's gonna be x minus x, starting with the ending point, going to the starting point, and then vice versa, or not vice versa, but do it the same thing with the y's.
So it's like the slope formula, but instead of adding, it's subtracting. So
Yes, yeah.
like the line 2 is plus.
Yeah, yeah.
You're just subtracting.
I guess, but like when I'm doing the slope formula, I actually start with this point.
Oh.
It doesn't matter. With slope formula, it doesn't matter which point you start with. This one it does matter, so that's important. Does everybody understand that? So you could do it graphically, that's fine. Or you could do it algebraically, which is quicker, but don't mess up. Okay? That's vector component form. Then we talked about finding magnitude and direction. So if you have a vector in component form, x, y, you have a vector in component form, the formulas are actually exactly the same as the polar coordinate formulas when you change into polar form. This is the formula to find the magnitude, and this is the formula to find the direction. It's exactly the same. The magnitude is the square root of x squared plus y squared. And the direction is the angle whose tangent is y over x. And again, careful, because possible you might have it pointing the wrong direction. You gotta make sure that it's not just giving you the reference angle, but the actual angle. Okay? Any questions on that? And then finally, we just did like simple operations on vectors, like adding and subtracting vectors. You literally just add and subtract their components. That's it. Graphically, how that works is like the tip to tail thing, right? So like if you have a vector added to another vector, its sum would be like this vector here. That's like the sum of the two vectors. You remember that stuff? And subtracting is like multiplying by a -1 scalar and then adding the two. So I should include this as another topic. Multiplying by a scalar. You literally just distribute into the components, right? If you're multiplying by 2, you multiply each component by 2. What does multiplying by a scalar do to the magnitude of the vector? It just multiplies the magnitude by that same number. Like if you multiply by a scalar of 2, it makes it twice as long, but it's pointing the same way. If you multiply by a -2, it makes the vector that's twice as long, but it's pointing the opposite way, 180 degrees. You guys remember that stuff?
Yeah.
Kind of? Yeah,
Okay,
question.
so this was kind of a weird question, but with the direction thing where, like, you don't know if it's pointing the right way or not, like,
Yeah.
Mathematically, is there a way to, like, mathematically find that out? Like, obviously,
Yeah.
we can compare it, like,
Yeah,
but is there a
if,
way to do that?
yeah, if the components are a first or, I think, yeah, a first or a fourth quadrant angle, like if the components get you into the first or fourth quadrant, then you're gonna get an answer that's correct. If it's a second or third quadrant, like direction vector, then it's gonna give you the wrong answer. So that's kind of the
So
basis
if
of
it
it.
has, like, a negative x.
Yeah,
Okay.
yeah, that's a good way to think. That's more succinct than what I said. Yes, that's exactly right. Okay, and the reason for that is like, it's a little like in the weeds, but the reason for that is because if you consider an inverse tangent graph, like I know what the tangent graph looks like. You all should know what the tangent graph looks like from last year. It kind of looks like this. Do you sort of remember something like this from last year?
Yeah.
You probably didn't spend a lot of time on it, but that's roughly what the tangent graph looks like. It has these asymptotes and it approaches these asymptotes. So if you consider what the graph of inverse tangent looks like, this is tangent x. The inverse graph, you reflect over the diagonal, right? So the inverse graph actually looks like this. It's super weird. It's just kind of sideways. And it has these same asymptotes, but now they're sideways asymptotes. It kind of looks like that, right? Does that make sense? That if that's the graph, this is its inverse?
Yeah.
And the problem with this graph is it's not a function. How do I know it's not a function?
Because of the vertical line.
Yeah, it fails miserably, right? This would, every vertical line you draw would fail the vertical line test, right? So what they do is they actually just say, like, mathematicians in ancient times were like, I don't really like the fact that this isn't a function, so I'm just gonna count part of it. I'm only gonna count this part of it. And we're gonna call that the inverse function, tangent inverse, okay? And if you think about where this is defined, these asymptotes occur whenever cosine is 0, right? Because tangent is sine over cosine, and if the denominator is 0, then the function's undefined, right? So if cosine is 0, we know it's 0 at like 90, and this one would be like 270, and this is negative 90, and so on.
Oh, that's neat.
Then these points correspond to negative 90 and 90 and 270 because you're switching x's and y's, right? So basically what I'm saying is this yellow curve only exists between negative 90 degrees and positive 90 degrees. Well, where is negative 90 to positive 90? It's in these two quadrants right here. Does that make sense?
Yeah, that's really interesting.
So when you take inverse tangent on your calculator, it's never going to give you any answer other than something between negative 90 and positive 90.
Would there be like a way where you could, like, I don't know, account for the rest of the inverse of tangent? Or
Yeah, reference angles. And so
Yeah.
that's what we do. Yeah.
Huh.
But you don't want your calculator to be like, oh, the answer could be this or this or this or this or that. That would be way confusing. So your calculator just gives you the reference angle and says, do with it what you want, right? So that's kind of the reason. You know, you're definitely not responsible for that type of stuff, but
multiple choice questions.
yeah. All right, so that's unit 2. Any questions on that stuff? So it's really not that much stuff in unit 2. It's just a couple things about polar, a couple things about vectors, and the vector stuff maybe you've seen in science or physics or something like that before. I'm not sure, but
We basically
Yeah.
did the same stuff.
so I think unit 2 was kind of easy. Somebody asked me yesterday, like, what's the order of like things on the test? Like on Friday, next Friday, the 18th, the test is going to be like on unit 1, 2, and then part of 3. And then on Monday, it's going to be like the rest of 3 and 4 and 5. So I just cut it in half, like,
Just
right?
in order, yeah.
It's not all mixed up, like it could be anything either day. So you can sort of
You
focus
know
on
what.
one thing.
Okay.
Any questions?
Wait, each test is gonna be like 12, 15 questions, like the one we take.
Yeah, each test is going to be kind of like that review assignment that you did on unit 1. It's just going to be like, a question here, a question there on those same topics.
Okay.
Okay?
Yep.
All right, I'm going to stop recording. The homework's just called unit 2 review. That's it.